Welcome to The Explainer. I am absolutely thrilled to have you here today because, honestly, we're about to unpack a hidden, totally microscopic universe that literally dictates how our modern world operates. I mean, we're surrounded by billions of tiny, invisible brains that silently run everything, from the vehicles we drive right down to the appliances in our kitchens. Today, we're pulling back the curtain on the invisible world of firmware and embedded systems. Let's get into it.
Okay, let's dive into this. Have you ever actually stopped to wonder how your coffee machine knows the exact moment to stop pouring your morning brew? Or, how your refrigerator knows precisely when to kick on the cooling compressor? It's not magic, and it's definitely not a standard computer like the one sitting on your desk. These devices are powered by embedded systems. These are small, incredibly dedicated computers designed to perform very specific tasks with absolute unfailing reliability. And the intelligence bringing those systems to life is exactly what we're going to explore today. To really grasp these tiny brains, we first need to define what they're actually thinking with. And we call this firmware. Firmware is essentially software for hardware. It's embedded directly into the hardware devices themselves, providing the fundamental instructions that help the hardware start up, communicate, and function. You can think of it as being fundamentally different from the software or apps you interact with on your phone or laptop. I mean, you don't browse the internet on your coffee machine, right? Firmware is low-level, highly specific, and intrinsically tied to the physical components it controls. So, here's our roadmap for today's explainer. We're going to look at the software for hardware, check out the anatomy of a microcontroller, move from bare metal environments to full operating systems, explore the intense art of debugging, and finally talk about how we secured this invisible world. It's going to be a great ride.
All right, let's kick things off with Section 1, the software for hardware.
Every single embedded system out there, no matter how complex, fundamentally interacts with the physical world using a really simple but incredibly powerful logic cycle: sense, process, act. First, the device gathers information from the environment using sensors. Maybe it's measuring a change in temperature or detecting a button press. Second, it processes that data. It uses the firmware's programmed logic to decide what to do with that new information. Finally, it acts. It triggers a physical response, like turning on a motor, closing a valve, or just lighting up an LED. This loop right here is the absolute foundation of how firmware bridges the gap between digital code and our physical reality.
Moving right along to Section 2, Anatomy of a Microcontroller.
Now, what's really interesting about this slide is where the firmware actually lives. We have to look at the physical stage. You're probably familiar with a microprocessor. That's the CPU inside your laptop. But a microprocessor is just a processor. It actually requires external memory chips and external peripherals to do anything useful. A microcontroller, on the other hand, that is a fully self-contained tiny computer on a chip. It's got the CPU, the memory, and all the communication peripherals built right into one single piece of silicon. It is highly optimized for control tasks, which makes it the absolute perfect home for our firmware. Inside that tiny microcontroller, memory is usually split into two main camps: flash memory and RAM. Flash memory is where your firmware code permanently lives. It's non-volatile, which just means when you unplug your smart plug from the wall, it doesn't suddenly forget its instructions. RAM, on the other hand, is the dynamic workspace. It's used during program execution to hold temporary variables and track active tasks. And because microcontrollers are heavily resource-constrained, developers might literally only have a few kilobytes of RAM to work with. That makes memory management an absolutely critical skill. But here's the thing. Nothing in this tiny computer happens without a heartbeat, and that heartbeat is provided by the clock tree. Microcontrollers are digital logic devices that rely on sequential logic. The clock tree distributes precise timing signals across the CPU and all of its peripherals, keeping billions of microscopic operations perfectly synchronized. It's like a conductor leading an orchestra. And managing this clock is also how developers manage power. By slowing down or turning off the clock to certain parts of the chip, a device can enter deep sleep modes and run on a tiny coin cell battery for years. Which brings us to Section 3, bare metal to operating systems.
And this brilliantly illustrates the different environments developers use to actually run their code. There are three main approaches. First, there's bare metal. This is exactly what it sounds like. There's no operating system at all, just your code running in an infinite loop directly on the hardware itself. It's got a super low memory footprint and is perfect for simple tasks. Then we step up to an RTOS, or a real-time operating system. This adds lightweight multitasking, allowing developers to split code into independent tasks with strict timing guarantees. That is vital for something like a medical device or a drone where timing is literally life or death.
Finally, for highly complex systems with displays or heavy networking, you might use a full embedded OS, like Linux. Regardless of the environment you choose, your software ultimately has to talk to the physical hardware, and that is done through drivers. You see, writing firmware means doing a ton of raw, low-level register math and bit manipulation. Drivers abstract all that incredibly complex hardware math away. By designing robust drivers, a developer can just write a simple, high-level command like read_temperature, and the driver translates that into the precise sequence of electrical signals the hardware actually needs. This decoupling makes code clean, reusable, and super portable. Now for Section 4, the art of debugging. When you write web software and there's a bug, you might get an error message on a screen. But when you write firmware, the physical hardware does something unexpected or fails entirely. The stakes here can be astronomical, literally. Think about this. During the Apollo 11 moon landing, the onboard computer actually began throwing alarms because of a task overflow. It was being fed way too much radar data. Thankfully, the system was brilliantly designed to restart and prioritize crucial tasks, which allowed the mission to continue safely. But it perfectly highlights why rigorous debugging and forensics are absolute necessities when software meets physical reality. A bug here has immediate real-world consequences. To hunt down these invisible, potentially disastrous bugs, developers use some pretty intense forensic tools. UART logging allows them to output text directly over a serial cable. Hardware debuggers like JTAG and SWD let them physically pause the processor mid-stride and step through the code instruction by instruction. For advanced systems, tools like ARM CoreSight allow developers to trace code execution in real time without actually pausing the system. It's like looking inside the chip's brain while it's fully alive. And when things crash mysteriously, developers will pore over map and disassembly files to analyze the exact memory layout just to figure out where things went off the rails. So, what kind of bugs are they actually hunting for? Well, one of the most common, and definitely the most dangerous, is the buffer overflow. Because memory is so incredibly constrained on these chips, if your firmware accidentally writes data past the end of an allocated array, it just silently overwrites the neighboring memory. This corrupts data, causes mysterious system crashes, and much worse, acts as a primary gateway for malicious actors to inject exploits right into the device. Let's pivot to our final topic, Section 5, Securing the Invisible World. This brings us to a really critical pivot point. As our devices become increasingly connected to the Internet of Things, firmware security is paramount. Hackers don't have to physically touch a device to compromise it anymore. They can do it over Wi-Fi or Bluetooth. To defend against this, developers absolutely must implement layered security. This includes things like Secure Boot, which ensures the hardware will only run cryptographically signed, trusted firmware. It means encrypting over-the-air updates so attackers can intercept and modify the patches. It means permanently locking those JTAG debug interfaces once the product leaves the factory, and disabling any unused peripherals to shrink the attack surface. In a connected network, just a single insecure smart plug can be the backdoor that compromises an entire enterprise. So the crucial point here is that firmware vulnerabilities are absolutely not just theoretical. They have massive physical consequences. We've actually seen this play out on the world stage. A notorious cyber attack on the Ukrainian power grid didn't just remotely turn off switches. The attackers deliberately targeted the firmware itself. By overwriting the firmware on serial to Ethernet converters with malicious code, they permanently bricked the hardware, rendering it totally inoperable and deeply complicating the recovery of the power grid. Firmware security really is national security. We've covered the software logic, the hardware anatomy of microcontrollers, the environments they run in, and the really intense stakes of debugging and security. So I want to leave you with this final thought today. Take a second and just look around the room you are in right now. From your thermostat to your smartwatch to that router blinking in the corner, how many of these invisible brains are silently sensing, processing, and acting right now? It's a totally fascinating, super complex, and high-stakes invisible world. Thank you so much for joining me on this explainer, and keep your curiosity switched on.